What we're going to look at is some relationships between sides and angles of triangles. So what I want you to do first is I want you to take a look at the warm-up, and I just want you to think about if you look at these objects over here, these little rods and whatnot, if you look at those, and if you were to pick three of those rods of different colors and different sizes, which three could you pick to form a triangle, and how do you know? So take a second to pause the video and just think about that. There's more than one right answer. So just go ahead, pause the video, and take a thought, take a think. All right, so looking at these, you might have said that you could make a triangle if you took a red shape, another red shape, and then maybe a yellow shape. You can obviously see if you're looking at this figure that they already made a triangle out of, a red, a blue, and a green. Does that work? Okay, so red, blue, and green, it kind of looks like they made a triangle out of that. Now, the question of how do you know, you might not know right now how you know. You might, your reason for knowing might be I would need to take those three rods and put them together to see if they make a triangle. So what we're going to look at today is how do we know if three different rods or three different sides of a certain lengths make a triangle. So what we're going to look at today is, we could take these rods and we could build a triangle using one blue rod, one green rod, and one red rod. But then the question comes up, could we still build a triangle if we used a yellow rod instead of the green rod? Why or why not? Could you form a triangle with two yellow rods and one green rod? Okay, why or why not? Or what if you use two green rods and one yellow rod? So our question is, how can we determine which sets of three rods can be arranged into triangles and which can't? Okay, so right now our main question is, how can we determine which set of three rods, or in our case, three sides, can be arranged into a triangle and which can't? How do we figure that out? What is the relationship? How do we know if three sides can be used to create a triangle? So what we're going to do is I want you to go ahead and pause the video. I want you to work on this investigation. I want you to construct triangle CAT from those three sides that are given to you, and then I want you to construct triangle FSH with the three sides that are given to you there. And then after you construct those, pause or unpause the video and watch my construction, and then we'll have a discussion. Okay, so we're going to jump over to the smartboard. We're going to construct triangle CAT. Remember, the first thing that you need to do whenever you're constructing something, constructing a shape, is you need to draw a side to start with. That gives you an endpoint to work with. So now what we're going to do is we're going to put the long side CT on the bottom. As you can see, my compass is almost stretched out as far as it can go to create this side, so we can construct side CT. After that, we have CAT, so we need to go over here and duplicate side, we'll duplicate side CA. Okay, we'll start with C here since C is connected to, C is our starting endpoint over here, so we have CA, which is this length. We're going to come here and start with our point on point C, and whoops, and this is why using a regular compass instead of a computer compass is better, because you don't have accidental clicks. So okay, apparently my compass didn't adjust size, so we're going to make a arc right here. Okay, after we create that arc, we're going to then create side AT. Side AT would start over here on this other point that we created, which was this over here is point T. We're going to construct an arc here, and what we'll see is that we have a point of intersection for those two arcs. So what that means is that we can draw a triangle from point C up to point A, and then from point A over to point T. And so we've constructed triangle CAT. Okay, so we have C, A, and T. Now, what that tells us is that we could use these three sides and use them to construct a triangle. All right, so now take a look at FSH. So we want to construct triangle FSH. So again, you're going to start by drawing in your initial side that you're going to, or your segment that you're going to use, or your ray. Let's go ahead and put FS on this side right here. So we have F is where our pointy end is. So we'll go ahead and label that ahead of time here. So here's F, and here's S. Now we're going to go about our same thing, or same process. We're going to create SH. So SH would be this long, and we need to put the pointy end right here, adjust our compass to over here, and create our arc. Then we're going to go ahead and get FH, adjust our compass, put it right here, and create our arc. And what you should notice here is that these two arcs do not intersect. So what that means is that there is no place for us to put point H, because point H needs to be the same distance, or needs to match up. It needs to be this distance from S and this distance from F, and since there's no place where these arcs intersect, that means that there is no point H that we can put on here that would be the correct distance from F and the correct distance from S. So that means that you cannot construct this triangle. So let's go ahead and we're going to jump back to our notes. So we found out that on construct CAT, triangle CAT, we can do this. All right. But with triangle FSH, we can't do this. Can't construct. Okay? And we want to talk about, well, why couldn't we construct this? Why would we not be able to construct this this triangle FSH? And what happens is, if we were to go back and take a look at this, here's FS. So if we look at this, we have FS, and we have, let's just take a look at what happens here. If we check the distances of FS compared to SH and FH combined. So if we take a look at this, we go here, and then we have FH. Should be right here. Okay. So if we look at the two distances of those shorter sides, we notice that they are not as long as our longest side, FS. Now, if we come over here and we were to check these two sides, let's check the two shorter sides and see what happens. If we look at AT first, so we put AT here, and then let's take a look if what happens if we add on to that and add on CA. So if we add on CA, come here, and you'll notice that if we look at the sum of CA and AT, that distance is longer than the side CT. So what that leads us to come up with is this idea of a triangle inequality conjecture. And what the triangle inequality conjecture states is that the sum of the lengths of any two sides of a triangle is greater than the length of the third side. So what that means is, if you take any two sides and you add them together, those two sides should be bigger than the length of the third side. Okay? So, why is this true? If you think about the saying, the shortest path between 2 points is along the segment connecting them, what that means is that the path from A to C to B can't be shorter than the path from A to B. All right? So what that means is if we have triangle A, B, and C, so A, B, and C, we know that the distance from A to C is the shortest distance between those 2 points because it's on a straight path, okay? It's on the segment connecting them. So what that means is that the distance AB plus BC has to be longer than AC, okay? And you can take that the other way. We know that the distance from B to C is the shortest distance from B to C. So that means that if you take BA, that distance, and AC, that distance has to be longer than the distance between BC. Okay? So again, the triangle inequality conjecture states that if you take the lengths of any two sides of a triangle and add them together, they have to be greater than the third side. In this case, if we had distances here, what would happen is, for instance, you might have something that says like 11, 5, and 4. Okay? And so if you take 5 and 4 and add that, 5 plus 4 is equal to 9. 9 is not greater than 11. So because 9 is not greater than 11, we can't construct that triangle. So the next thing that we want to look at is we want to find out, can we determine where the largest and smallest angles are going to lie in a triangle? Now, if we were all together in class, we would pull out some protractors and patty paper and draw some triangles and compare our answers with each other. But what we're going to do is we're going to take a look at a activity on Desmos to do this investigation together. So what you would do is you would create some triangles. Everyone in your group would draw a different scalene triangle, meaning your sides of your triangles would all be different sizes. And then you would go through and answer these questions. You would measure your angles. Okay, so if you want to do this at home, feel free. Measure your angles in your triangle, and then you would label the angle with the greatest measure, angle L, the greatest with the angle with the second greatest measure, angle M, and the smallest angle you would label angle S. Then you would measure the three sides. You would label the longest side L, the second longest side little m, and the shortest side little s. And then what you want to take a look at is, do you notice anything about which side is opposite which angle? So let's take a second to look at this on Desmos. I have a bunch of triangles here. All the sides on these triangles are different, so we don't have any isosceles triangles. We have a bunch of scalene triangles. And what I want you to take a look at is, what do you notice about the side lengths and the angle lengths? And if you take a look at this, you'll notice, if we look at this triangle over here, this one with a 116-degree angle, you'll notice that the side across from that is 6.99. You'll notice that the side across from 38 is 4.75. And then the side across from 26 is 3.45. Then you'd notice that the side across from 44 over here is 4.09. The side across from 61-degree angle is 5.12. The side across from a 74-degree angle is 5.62. So if we were to list these out, okay, if we were to take this, and I'm going to draw one of these on our on my notes. So we'll use this one. So I'm going to draw this 116-degree angle in my notes. 6.99. We had 38 degrees over here. That was 4.75. And then 26 degrees over here. That was 3.45. So let's jump back over to our notes. So if you look at this triangle and we were to go ahead and look at which side is opposite angle L. So it said label our greatest measure angle L. So here's angle L. And then we had angle, our second was the angle M, and then angle S. And then if we side L, side S, and side M. So if we take a look at this, angle L has side L across from it. Angle M has side M across from it, and angle S has side S across from it. So if you look at this, what do you notice? The largest angle, 116 degrees, has the largest side across from it. The second greatest angle, set 38 degrees, angle M, has the second longest side across from it. And then the smallest angle has the smallest side across from it. So what we can say here is we have this side angle inequality conjecture. It says in a triangle, if one side is longer than another side, then the angle opposite the longer side is greater than, or is larger than the angle opposite the shorter side. Okay. Now, what we can say here is this. Okay, and I'm gonna simplify this conjecture for us. So the conclusion that we can say is largest angle has the largest side across from it. Middle angle, and this isn't really what it's called, but the second largest angle, we're going to call it the middle angle, has the middle side, the middle size side across from it. And finally, the smallest angle has the smallest side across from it. And look, if this is not true, if the largest angle if the largest angle has the smallest side across from it in a picture of your triangle, that means that that triangle does not exist. That is not possible. Okay, so the largest angle has to have the largest side across from it. So let me give you an example of something that would not be possible. Let's say we had this picture right here. Okay, I'm looking at this picture that is already drawn here. If this was 120 degrees, this was 30 degrees, and this was 50 or 30. This was hold on. Say this was 20 degrees, and this was 40 degrees over here. Okay. This means that if you had a picture and it said this was 8, and this was 2, and this was 10. This picture of this triangle is not possible. Okay, it is not possible because we know from the triangle inequality conjecture, or the side angle inequality conjecture, we know that the longest side has to be across from the biggest angle. And in this case, the longest side is 10, and it's not across from the largest angle. So this triangle is not an actual triangle. It's not possible. There's something wrong with that drawing. Okay, so we've gone over the triangle inequality conjecture. We've gone over the side angle inequality conjecture. We have one more conjecture to figure out, but what I want to do is take a second to talk about these vocab words up here. Okay, so let's say you have a triangle that has a ray that extends out past the triangle. This angle right here on the outside of that triangle is called an exterior angle. So an angle that forms a linear pair with one of the interior angles of a polygon is called an exterior angle at that vertex. Okay? So in this chapter, what we have studied so far is the interior angles of triangles. We've learned that they add up to 180 degrees, and then we figured out some relationships for isosceles triangles and their angles on the inside. So triangles also have these exterior angles. And again, so if you extend a line out past one of your interior angles and create a linear pair, you get an exterior angle. Now, each exterior angle of a triangle has an adjacent interior angle. That is the angle that is right next to the exterior angle. It is the angle that creates the linear pair. Okay, so it is the angle that creates the linear pair with the exterior angle. All right. Then you also have a pair of remote interior angles. The remote interior angles are the two angles in the triangle that do not share a vertex with the exterior angle. So it is the angles that are not forming a linear pair with your exterior angle. Okay? So there is a relationship between some of the angles and your exterior angle. And what we want to do is we want to take a second to figure that out. So we could walk through this investigation, but instead of doing that, we're going to take a second to look at it on Desmos. So if we jump over here, we have a triangle right here with an exterior angle created with this angle down here that's 56 degrees. So 56 plus 124 gives us that linear pair of 180 degrees. And what I want you to do is I want you to see if you notice a relationship between this angle, that's 124 degrees, and these two angles. So if you look at this, 68 plus 56, if you added those together, you would get 124. If I adjust this right here, if we look at this, I've adjusted this exterior angle. I've changed the angles a little bit in this triangle. If we look at 38 plus 79, that would give us 117. If we adjust this a little bit more, if we look at 54 plus 83, that would give us 137. If we look at this one, if we have 44 plus 83, that would give us 127. If we look at this, 33 plus 42 would give us 75. So this is our adjacent interior angle, and these two over here are our remote interior angles. What have we noticed about these two remote interior angles and this exterior angle? 33 plus 42 is 75. If we look at this one, 40 plus 67 is 107. So what you should notice is no matter what, whatever your remote interior angles are, they are going to sum up to that exterior angle on that opposite side. So if we jump back over to our notes, the measure of an exterior angle of a triangle is equal to, the measure, or the sum, the sum of the remote interior angles. Okay? So again, what that means is this angle, this exterior angle, is equal to the sum of A plus C. Now, if we wanted to prove this conjecture, because remember, we made this conjecture based off of observations. If we wanted to prove that this conjecture was correct, we would need to use deductive reasoning. So let's think about this. Let's think about how we could prove this. What do we know about the sum of the interior angles? We know that the sum of the interior angles is equal to 180 degrees. So A plus B plus C is equal to 180 degrees. That's true for all triangles. C and D create a linear pair. And we know that if we take the sum of those two angles, since they're a linear pair, it also gives us 180 degrees. Now, because A plus B plus C equals 180 and C plus D equals 180, we can say that A plus B plus C is equal to C plus D. With a little bit of algebra, we subtract C from both sides, we get A plus B equals D. Take a look at that. That is exactly what we just said in our conjecture. We said angle D, the exterior angle, is equal to the sum of the remote interior angles, A and B. A plus B equals D. So we have just proved using deductive reasoning, using algebra here, to show that that is in fact a true conjecture every time, regardless of what the triangle is, or regardless of the size of the angles. So now we can take this and we know that that is true forever. So before we end the notes, I want to look at a few examples here just so you can see what types of problems you might be expected to do. In this first example, it says find the value of x. So if we want to find the value of x right here, we can use our idea of linear pairs here. If this is 100 degrees, we know that this angle would have to be 80 degrees. If that's 80 degrees, we have to know this is 100 degrees. So we have 100 degrees and 30 degrees. That's 150 degrees. And we know that the entire triangle would have to be 180 degrees. 180 minus 150 is 30 degrees. So we know x is equal to 30 degrees. Down in this next question, it says the lengths of two sides of a triangle are 11 centimeters and 25 centimeters. Which of the following could be the length of the third side? So remember, we know that when we add two sides together, they have to be longer than the third side. So if could the third side be 14? The answer to that is no, because 14 is so let's take a look at that. If we had 14 here, we would have 11 plus 25, or my fault, not 20, that's not 26, that's 36. So if we had that, we would have 11 plus 25 is 36. So if we had 11, 25, and 14, is 36 bigger than 14? Yes, okay, so that works. So let's check. If we took 11 plus 14, 11 plus 14 is 25. Is 25 bigger than 25? 25 is equal to 25. 25 is not greater than 25. So that means that 14 would not work, okay? 14 does not work because, again, if you add two sides, they have to be bigger than they have to be larger than the third side. So let's take a look at 25 centimeters. What if we had a triangle that was 11, 25, and 25? If we take these sides, 11 plus 25 is equal to 36. Is 36 bigger than 25? It is, so that works. Let's take 25. If we took both sides, 25 plus 25, that is 50. Is 50 bigger than the third side of 11? It is, so that works. And finally, we could take 11 plus 25 again. That's 36. 36 is bigger than 25. So it appears that B is our answer. Now, let's take a look. Let's make sure you understand everything. If we had the sides 11, 25, and 36, if you take 11 and add 25, that equals 36. 36 is not greater than 36. It is equal to 36. So, because these two sides added together are not bigger than the third side, that means that that cannot be a solution. And finally, if you look at 11, 25, and 45, if you add 11 plus 25, you get 36. 36 is less than 45. So again, remember, we said through that conjecture that these two sides, when added together, should be larger than larger than the third side. It is not, so that means that cannot be a solution. So you're going to go ahead and work on your homework right here. If you have any questions, message me on Remind or email me, and I'll be happy to get back to you.